Hi, and welcome to Modern Physics Lab 4 by Joseph Knopf. In this lab, we will be examining how a spring and its oscillations can demonstrate the conservation of energy. Essentially, the total energy of this system is going to be equal to the potential energy plus the kinetic energy. Now, the potential energy in the system is going to be equal to the gravitational potential energy plus the spring potential energy, whereas the kinetic is simply the kinetic energy. Thus, E equals mgh plus 1/2 the spring constant times x squared plus 1/2 mv squared. As well, we need to know the period. In this lab, I estimated the period simply by looking at my values in Tracker. And solving algebraically, I could then find the spring constant. Knowing the spring constant, I could then solve for the relaxed length of the spring shown here. Using Python, I was able to model the spring's motion through code. Here, I have all these values plugged in, just basic relationships that are needed so that I can run the next part of the code. This right here shows the energy equations: kinetic, gravitational potential, and spring potential. Now this is where the actual code happens. I established the value of the force of gravity and the force of the spring and the net force. Knowing this, I'm able to find the ball's velocity, which lets me find the ball's position. And this code essentially updates the values for each every 1/20th of a second, I believe. And here, this part updates the length and the L hat and the magnitude of the distance so that it can recalculate the spring potential over again. This down here calculates the difference in kinetic energy and the difference in the potential gravitational and the potential spring. What does it mean? Question number 1. Yes, the energy principle is satisfied. As you can see, this yellow line here represents the total energy of the system. And as you can see, it stays relatively the same, despite the huge oscillations in potential and gravitational potential and kinetic energy. Essentially, they are inverses of each other. As the total potential energy rises, the total kinetic energy will lower. What does it mean? Question number 2. The oscillation period I estimated to be the x direction oscillation period I estimated to be about 1.8033 seconds. And I determined this from estimating on Tracker. And for the y oscillation period, through the same methods, I determined it was about 1.48 seconds. Here you can see the difference in the positions of both the observed and the modeled motion. As you can tell, they are very similar. The only difference is that the modeled motion seems to be at a higher position than the observed position. The only reason I can think of for this is that I may have mismarked the Tracker file, and as well the spring in real life may have not had a exact stiffness that I predicted it to be.